morning. This is lecture 8. This is spatial lecture because of situation here. So we're talking about another type of antennas, which is called microstrip antennas. So please pay attention to this class because in term projects you will need to design this antenna. But it's going to be really easy design, and it's going to be pretty much, if you understand everything I say today, it will be very easy for you to do it. So let's talk about microstrip antennas a bit. This antenna, actually, people, scientists, let's say scientists or engineers in World War II, they developed this antenna to attach to rocket, to airplanes. It's supposed to be small and light, and they can attach to this antenna to any surface. So the cord is small, okay, and we call it conformal configuration, which just means that any kind of surface you can attach it on. So it will be like a thin piece of metal and dielectric substrate. So then compatible with integrated circuits, which means that you can use it as an interconnect to PCB, to electronic circuits, which is very easy compared to other types of antennas. And also, you could work in dual frequency range. Roughly, you could see 2 resonance frequencies when you look at the spectrum of microstrip antennas. Microstrip antenna radiation patterns is omnidirectional. But the drawback, because this antenna is supposed to be small, so they want to design it to be small, so it would provide very low efficiency, low power, and most of the time they will experience what's called spurious speed radiation. What this spurious speed radiation means that it's like a leaking of the fields into the air. It's not confined inside the antenna and radiate. Okay, so next is, let me check the materials here. All right, so next thing is basic characteristics. If you see this antenna consists of 3 layers. The first layer on the top is called patch, which is the conductive metallic material. And number 2 here in the middle is substrate. Substrate is made from insulators and is represented by this dielectric constants of epsilon r. And at the bottom, this is ground plane. So this is the usual ground plane. Now look at the size and dimensions. The characteristics of the antennas are defined by their dimensions, as you know. So in this type of antennas, we look at probably 1, 2, 3. Okay, as dimensional characteristics. The first one is the length of the patch, L. The second one is the width of the patch, and the third one is the thickness of the substrate. So if you vary these 3, you will vary the characteristic of the antennas. So normally, we would like this strip patch to interfere, not interfere. It's like we try not to let this microstrip patch to interfere with the signal propagation inside the antenna. So we make it thin. So how thin is it? The thickness of this patch. Okay, I'm sorry, I forgot to mention this T, which is the thickness of the patch. So the thickness of the patch is much less than the operational wavelength, lambda naught. And the substrate thickness, the edge here, is much smaller than the wavelength of the operational wavelength as well. So normally the thickness is between 0.003 lambda naught to 0.05 lambda naught, and then ground plane. Another criteria is rectangular patch. If you use a rectangular patch, the length is usually between lambda naught over 3 to lambda naught half. We'll see later in the design that the desirable design would be something close to lambda naught over 2 or lambda naught half. Okay, so here's pictures of microstrip antennas on the top wheel and side view. And you can see the thickness is here, and this is the thickness of the substrate. Okay, so decidable antenna substrates, usually we will design the dielectric constant. We choose the dielectric materials to have the constants between 2.2 to 12. And there's the difference in variations when we choose it. If you have thick substrate, usually they'll do thick substrate with low epsilon r because they want to increase the efficiency of the antenna. They want to increase the bandwidth, and this the fuse loosely bound means that the fuse are easily radiated into the space. Okay, so the drawback is larger element size when you have big substrate. Yeah, for sure, you're gonna have much bigger size of the antenna. And if you use thin substrates. Usually they use thin substrate for, they use high dielectric constant materials with and make it thin. And this is usually used for high frequency operations such as microwave circuits. This is good because you have smaller element size, but again, because the substrate is really thin, so it's not easy to confine. Again, it might be a bit difficult to confine the fuse inside the antenna, so you might experience greater losses. All right. So the idea is that, to me, when you use thick substrate for low epsilon r, so how could we explain about low epsilon r, high epsilon r? Low epsilon r is mean that the epsilon r just is the measure that tells you that this material is ready to accept the electric field. If you have low epsilon r, it means that if you apply the electric field into this material, it's not kind of like, it might have less ability to accept the electric field compared to high epsilon r. So that explains why we might need the thick substrate, so that we want to confine the fuse inside the substrate. Okay, but for high epsilon r, so we hope that we can really we want to accept this electric field into the material. So that's why they do it thin, because the epsilon r is high already. But again, like I said before, because the dimensions, the thin dielectric material could cause some losses, okay, of fuse into the space as well. Okay. Now look at the shapes of the radiating patch. You can see that there are a variety of patches. I think the first four are the ones that we use a lot, and in this lecture I will teach you how to design the rectangular patch. So we have square, we have rectangular, we have dipole, and we have circular. And also you can see some elliptical, triangular sectors, circle ring, and ring sectors. But yeah, the mechanisms, how to make radiation mechanism would be different for different shapes, and you might experience different radiation patterns from different shapes. Okay, and now let's look at the feeding methods. Usually there are four methods to feed the signal. When we say feeding, what I mean is that when you want to apply the signal into the microstrip, in order for the microstrip to radiate those fields into the air. So there are basically four methods. The first one on figure A is called microstrip line feed. The second one is the probe feed. The third one is called aperture coupling feed. And the last one is proximity coupling feed. So let's look at each one. So it's easy to match by controlling the inset position. So what is the inset position? Inset position is measured from the edge here to here, to this point. And again, when I said match, I think everyone should know by now what the match term means. It means that you want to match the impedance of the antenna to the feed. Okay, so we can adjust the matching by adjusting the inset position. Number three is inset It's easy to model. That means if you want to put this into the simulator, it's easy to create this kind of structures and that I want you to do. In the probably this is a term project, so probably in a month you will design this and then submit it as a term project. And what is the drawback? Spurious radiations increase with substrate thickness. As I said earlier, if you have thick substrate and the fuse the fuse kind of loose, okay, not tighten inside the antenna. So there's a possibility for the fuse to leak out of the substrate, and that is called spurious radiation. So it radiates somewhere else. Okay. The second one is called coaxial line feed. In the coaxial line feed, the things is friends. Again, we have ground plane. I have to show you this. We have ground plane. We have the electric substrate, and then we have a patch. But now we don't feed it from the side. We punch a hole in the substrate. Okay, and we put coaxial connector here, and then we put the feed line here. And then the signal runs through this hole up to the patch, and then the patch starts to radiate. So this kind of feeding methods is easy to fabricate. It's easy to match. So when they want to do the impedance matching, they just move this position of the coaxial connector around, okay, and until they get the matching. And then those spurious radiation, because the fuse is injected, let's say is injected from coaxial connector, which is confined, the fuse are confined inside this material, inside this metal, and then run through this hole up to the patch. So it's not easy for the fuse to leak out of the channel here. But the drawback, with this kind of line feed, they experience narrow bandwidth. So if you want to use microstrip line as a wide bandwidth antenna, with this feeding method, it might be difficult. Okay, and it's difficult to model. So when you do simulations, it might not be easy to create coaxial connectors and then do all these things. But anyway, we can simplify simulation, so this should not be a problem with your term project. The third one and the fourth one are kind of similar, so that's why I placed two of them in the same page. The third one is called aperture coupling feed. This is the difference. You could see that for the third one, we have two substrates and different types of dielectric materials. And they are separated by this ground plane. So the ground plane is placed between these two dielectric materials. So if this ground plane isolates the feed from the radiating elements, what I mean by that is that they put the feed line, okay, they put the feed line on the bottom material, okay, and then the radiating elements or the patch is on top of the top material. And you can see here, so this is a patch. Okay, so this is a patch, and this is the dotted line. Here is the feed line. So the feed line comes from the bottom material, and then there's a slot, okay, small slot here that is a channel for fuel to radiate or to propagate up to the patch. Okay, so these structures of this feeding method is difficult to fabricate. Okay, so it provides narrow bandwidth, but it's easier to model because you see everything is kind of like it's like a rectangles everywhere, so it's pretty easy to model. And because we separate the top and bottom materials by the ground plane, so another good thing is that we can optimize the radiations independently. Okay, then we can do things with feed lines, and it might not affect the patchings or the radiating element up here. The last one is called proximity coupled feed or coupling feed. This one, we have the ground plane, okay, in the bottom, and then we place two types of dielectric materials on top of the ground plane. And this type, both materials are in contact, and the feed lines come from the bottom one, and then the patch, which is the radiating element, is on the top one, something like this. With this kind of calculum feed method, again, it's difficult to fabricate. Okay, there are layers of layers, but they provide largest bandwidth, and it's easy to model because everything is nice and it's in rectangular shape, so you can just place layer over layer, okay, which is easy. And low spurious radiation, okay, but then you cannot optimize the radiation independently like the third one, okay, because the two materials here are connected to each other. Okay. Now, we'll move on to methods of analysis. We'll teach you how to design these antennas. There are three methods: transmission line, cavity, and full wave. If you want to really understand what's going on with the microstrip antennas, I suggest you go to cavity or full wave. Transmission line analysis will just give you an surface, kind of like not full insight, but just give you the feeling what it's like. Okay, what the characteristics should be. And it's the easiest methods of analysis. So I just go with this transmission line method. In transmission line model, we represent this patch antenna by two slots, separated by load impedance ZZ and transmission line length of L. So what I mean is that if you think of this patch as the transmission line, so this is like the impedance number 1. And this is like the slot here, the slot, what I call the slot. Yes, if you look at the side view. Okay, if you look at the side view, it's right here. It's this angle there, but from the side angle, it looks like you see the rectangular opening here, so we call it slot. And then this another on the end here is another radiating slot. So there's two slots, slot number 1 and slot number 2. So if you think of transmission line, this is like load with some impedance. This is another impedance here, and the patch itself makes itself look like a characteristic impedance called ZC. Okay, so the length L will adjust the characteristic impedance ZC. Now, with this kind of rectangular patch analysis, one thing that we have to understand is that, because I said earlier that we have to be aware of spurious radiation, okay, and that appears here. So with this patch is kind of exposed to the air, so the fuse kind of leak to the outside or to the edge of the patch antenna. So this is called fringing effect. Okay, so the amount of fringing is a function of patch dimension and substrate height. And therefore, in the design, we need to take this fringing effect into account before in the designs, and we will see shortly after this. Now, let's look at the side view of the microstrip line and how the fuse radiate inside the microstrip. Usually we will, if you have much wider width of the patch compared to the thickness of the substrate, and if this epsilon r is much greater than 1, so like I said earlier, if you have high epsilon r, it means it can accept the electric field more. So electric field lines will mostly concentrate in the substrate, something like this. Okay. But the field lines, if you understand electric fields, it produced from the metal or from the conductors, and then it will terminate on the ground. Okay, so plus minus thing. So these field lines can be generated from the top I use laser pointer, can be generated from the top of the patch and also from the bottom of the patch and also from the side of the patch. And every few lines will go down and be terminated on the ground plane, something like this. So you could see that some of the field lines are inside the dielectric material, but some of the field lines are in the air. Okay. So another thing that we notice from this phenomena is the microstrip line appears to be wider electrically compared to its physical dimensions. So this is the patch, but you can see that there the line just goes out and then extends the size of the patch. Not physically extend, but virtually extend the size of the patch. So it appears to be so that the patch appears to be wider than its physical dimension. Okay. So therefore, because there are two media involved here, one is the air and one is dielectric material. So we need to introduce the term called effective dielectric constant, which is combine the dielectric constant of the material and the air altogether. Okay. I want to show you this graph. Show you the graph of effective dielectric constants as a function of log frequency, such as 10 to the 9 Hertz, 10 to the 10, 10 to the 11, 10 to 12, and 10 to 13. If you have different types of materials, for example, we have dielectric constant from 2.3 to 10.2. This is how the effective dielectric constant changes over the frequency. So you could see that all materials, the effective dielectric constants increase, for all materials, and the rate, the increasing rate is higher for higher dielectric constant material, like this, and then all the effective dielectric constants will saturate, at some point, something like this. All right, but this graph could be explained, by mathematical equations, using this equation here. If we design the ratio of the width to the height, the width here is the width of the patch to the height of the thickness of the substrate. If this ratio is greater than 1, then you can use this equation to determine the effective dielectric constants. So S1R EFF is the effective one, and S1R is the original dielectric constant. Now let's talk about effective length. Since we know that there is a fringing effect, and therefore the length of the patch will appear to be wider electrically than its physical dimensions. So we need to approximate this fringing length, which is called delta L. Delta L. That means the total length, including the electrical length, the fringing effect, is L plus 2 delta L. So L is the physical length plus 2 delta L from fringing. And the relation between delta L and H can be expressed using this equation. So in your design, you have to take this into account. You need to calculate this delta L in order to determine the actual dimension of the patch. Another thing that happens here is resonant frequency or operating frequency. If we treat the microstrip line or the patch as the slot, it looks like a cavity, three-dimensional cavity. So we will just focus on the dominant mode, which is called TM010. So I guess if you learn microwave engineering, that's one section in waveguides that talk about cavity. And thus we have the three number mode because it includes X, Y, and Z directions. So for dominant mode, we will focus on L equals lambda over 2, which is probably the best, I guess the best design would be designed as L equals lambda over 2. So we look at the resonant frequency without fringings. If there is no fringing, then your resonant frequency could be found by using this equation 1 over 2L square root epsilon R square root mu naught and epsilon naught. So this is the free space property which corresponds to light speed V naught. Okay, light speed. This is 3 times 10 to the 8 meter per second. But if you include the fringing or edge effects, then your L here will become L effective. The epsilon R here will become the epsilon R effective. And therefore, things will change, and the ratio between operating frequency or resonant frequency without and with fringing effects, okay, this is called fringe factor, which is defined as the resonant frequency, including fringings, divided by the resonant frequency without fringing. Okay, so that tells you about the what's called both effective dielectric constants that you have to include. It involves new design. Delta L involves new design, and also this resonant frequency. Okay. Now, this part is the design of microstrip antenna. So when let me tell you the okay, hold on, back in the half. Okay, so So let's assume you want to build this microstrip antenna. So what you need to know? The first thing is that you need to know the frequency, the operating frequency. Okay, and then you need to buy some substrate. So when you buy a substrate, in commercial substrate, usually in their data sheet, they usually provide the dielectric constant or epsilon R, and they usually come with the exact size, like the thickness, the exact certain thickness. So first step is that you need to know this material. Okay, you need to use the proper material or the materials that you want, and that will give you epsilon R effective, the thickness, and then you need to know operating frequency in hertz. And then we need to find the width and the length of the patch. So this is design procedure. We have to assume that our microstrip antenna is a good radiator. So with that assumption, we will find the width of the antenna using this equation. And then we will determine the effective dielectric constant, and then we determine the delta L, and finally we determine the actual length. Just focus on the procedures, the item 4 here. So usually, like I said, the best size, okay, that the people, the engineers or designer who wants, is close to lambda over 2. So that means the total effective length here usually would be lambda over 2, and then minus 2 delta L here, and then you get the actual length of the microstrip patch. So let's go to the example 1, and we will design this rectangular microstrip antenna together. Okay, so in this design, we have the substrate with the epsilon R of 2.2, H is 0.1588 centimeters, and raising it at 10 gigahertz. So example 1, the substrate, the epsilon R is 2.2, and the thickness is 0.1588 centimeters, and the frequency is 10 gigahertz. Okay, so we will assume that this antenna is a good radiator. So first we can find W. Okay, so our W, if you look at the equations, this is 1 over 2 FR square root of mu naught epsilon naught square root 2 epsilon r plus 1. Okay, so 1 over 2 here times 10 to the 9, and square root of mu naught epsilon naught is light speed. So 3 times 10 to the 8. Multiplied by the square root of 2 over 2.2 plus 1. Okay, so the total here is, let me check if I have this correctly. 10 to the 9. Okay, so you have the width of 1.01186 meters or 1.186 centimeters. Okay, so it depends on where you're from. Mostly in US, people will refer to the size using refer to the dimensions using inch and foot or feet. But in metrics, we use meters and centimeters. So I just stick with the centimeters and meters unit. And number 2, what we have to do is find the effective dielectric constant. Okay. So we have epsilon r plus 1 over 2 plus epsilon r minus 1, 2 multiplied by 1 plus 12h over w. Okay. So this becomes 2.2 plus 1 over 2 plus 2.2 minus 1 over 2, 1 plus 12. H is 0.1588 centimeters, and this is 1.186 centimeters. Okay, and the answer is 1.972. Okay, 1.972. Number 3, we need to find the extended incremental length of the path. So we want to find delta L. Okay. So in our equation, in our formula, okay, we use this formula delta L over H, which is 0.412. Epsilon R effective is 1.972. Okay, and then plus 0.3. Okay, and then W over H is 1.186 divided by 0.1588 plus 0.264. Okay, and then epsilon r effective minus 0.258. This is 1.1, and then W over H 1.186 over 0.1588 plus 0.8. Okay, and that you have delta L. Okay, and this is 0.1588 centimeters. You have delta L of 0.081 centimeter. Okay, so this is your extended length. Okay, like I said, the optimal length is lambda over 2. So the actual length, okay, LA actual, okay, could be I should say, let me go with the effective length first. So our effective length is lambda over 2. Okay, so lambda here is 10 is c over f. So this becomes z over 2f. Okay, so 3 times 10 to the 8 over 2 times 10 to the times 10 times 10 to the 9. Okay, and then we have 1.68 centimeters. Okay, so that means our L actual, so let me move it here. Our L actual is then L effective minus 2 of delta L. So why is it 2? Because there are two sides, the opening and the end of the patch. So we have 1.0868 centimeters minus 2 multiplied by 0.089. Okay. 162.6 centimeters. Okay. So this is done. Then you see now we have W and then we have L. Okay, so this considered as the end of the finish of the design. So if you draw the dimensions of the patch, okay, the patch would be look like this. Okay, so this is the length, 0.09, and this is the width, 1.186. Okay, and then this is the feeding direction. All right. So that's the example one. I guess if you are assigned the homework, and then in our homework or in actual intern projects that you will be assigned, it will involve something like this. So you will use this formula to design your microstrip antenna. Okay. อันนี้กลับมาที่นะคะ Okay. All right. Now let's consider the feeding line or inset position. Okay. I'll just take you to the end. Okay. I want to understand how to set this inset position. Okay, this inset position. Where we should put it, okay, to make it match, okay, to the patch. So we need to understand the concept of the equivalent circuit. Again, if we assume the antenna as the transmission line where the radiating slot, okay, at the opening is here, and the radiating slot at the end of the terminal of the lid of the antenna is here. Then we can draw the equivalent circuit, okay, and it contains this conductance G and susceptance B1. So let me write down the names of B and G and Y. Okay. So Y is called admittance. Okay, the unit is mho, which is the opposite to ohms. Okay, and G is conductance. Okay, and this is the opposite to R or resistance. And B is susceptance. This is opposite to reactance. Okay, so this is kind of, let me see, Z. Okay, so I use this arrow to represent the opposite. G is opposite to R, and then B is opposite to X. Okay, so if you admittance, you could write in terms of G plus JB. Same here, if you write it in impedance, you can write it in terms of R plus JX, something like this. Okay, so in this case of our equivalent circuit, okay, we represent this radiating slot by admittance. Okay, because it's easier this way. Think of combining the components. If you connect electrical components in series and parallel, if you connect it in parallel, it's usually easier to combine them or to find a total impedance by just series combine their admittance, okay, and then convert it back to impedance later, okay. So in this case, both radiating slots are connected in parallel. So that's why we choose admittance and to be used in our analysis here. The patch is represented by another admittance called YC. Okay. And this G1, Y1, which is the admittance of radiating slot 1, is G1 plus JB1. Each term could be represented by this equation. Okay. G1 is W over 120 lambda naught and multiplied by 1 minus 1 over 24 K naught H squared. So what is this K naught? K naught is called wave number. Alright. So K naught is the wave number, and you see the naught or the zero subscript over here, which is represent the wave number in free space. In free space, so it could be written as 2 pi over lambda naught. Okay, and you might, if you still remember, you might be curious. Was the difference between K naught and beta is actually the same. Okay, if we talk about free space, they're actually the same, but they just use the different symbols to represent it. Okay, now in G1 there's a condition though. The condition says that in order to use this equation, the thickness of the substrate over operating ref length must be less than 1/10. Usually that's the case, so it should be no problem. And B1, okay, is represented by this equation with the same condition. Okay, so keep this in mind because this is the same antenna. Okay, this is the same antenna. So therefore, if you look at Y2, okay, which is right here, it's the same antenna. They have same W, they have same lambda naught, they have same K, and they have same H. So Y2 equals Y1. G2 is then equal to G1, and B2 is then equal to B1. Right? So now, if you want to transform the admittance of slot 2, okay, the two input admittance of slot number 1, and we'll do conjugate matchings. Why we need to do this? Because we want to determine the input resistance to the patch at the resonant conditions or at resonant frequency. And this can be achieved if two slots are separated by lambda over 2. And this comes to realizations why we want the optimal length of lambda over 2. So if you learned transmission line theory before, you know that if the transmission line has the length of lambda over 2, the load impedance will be equal to the input impedance. And that's the point. So we want to do matchings then to make sure that the radiating slot number 2 equal to radiating slot number 1. And again, in matchings, we have to eliminate the susceptance or the imaginary part, so that's why we need to use conjugate matching. Okay, so for conjugate matchings, well, we need to, in order to match radiating slot number 2 and slot number 1, okay, the matchings will make this the transformations of radiating slot number 2 admittance to be equal to G1 minus JB1. So the original is G2 plus JB2, but after transformations, after matching, it will be equal to G1 minus JB1. So that when you series combine the admittance, you will have left with only conductance, okay, only conductance, and you can eliminate, okay, you can just delete this susceptance. Okay, so this is another reason that why we use admittance, because okay, you see that these both radiating slots are connected in parallel. So in terms of matchings, in terms of combines, this admittance, you can just combine it straightforwardly or directly. Okay, and there we go. After matchings, you will find that G2 will be equal to G1, and then you delete this, so B2 equals minus B1. Okay, and therefore the input impedance, or sorry, the input admittance at the resonant frequency will be Y1 plus Y2, and then tilde here, equals to G1. Okay. And therefore, the resonant input impedance, Zn, which is 1 over Yn, okay, will be equal to the real part, which is Rn, and it's equal to 1 over 2 G1. Okay. The Rns is unavoidable, okay, to have mutual effect between the slots, okay, in reality, but in theory, such as in practice problem, I will just take this mutual effect away. So, but in reality, there will be mutual effect between the slots. So this Rn here will be transformed again, and it will be equal. You have to add the effect of mutual conductance between two slots here. Okay, and then plus and minus here is promoted with odd, even, Brayton voltage distributions. Okay, that you will not have to understand it in this class. And then you can find mutual conductance. Okay, using these equations. E1 is radiated by slot number 1, H2 is radiated by slot number 2, and then V0 is the voltage across the slot. So at this point, I think just to get you to see it, and then just like your exposure, but we're not going to use it in our exam or in our homework. And then in order to find G12, there's rigorous derivations, but finally we can find G12 using this integration, okay, and some functions. Now, the input resistance facts, again, why do we need to know the input resistance? So because if we know the input resistance, we can understand how to match the feed line. Okay, for example, if you want to set the inset, like in these pictures, like I said earlier, the inset position determines the matching. Okay, so if you know the input resistance of the patch, then you can control the inset position here to match with the input resistance of the patch. But the fact is that the facts are that the input resistance is not strongly dependent of the substrate height. That means if you change the height of the substrate, you might not see the variations of resistance. But it varied mostly by the width of the patch. As you can see, I think these equations, you see there's this W, okay, is in front of the parenthesis of the bracket. But K0 and H is inside, and that divided by 24, and here 0.636. So that's why H is not so not so involved or not so concerned in input resistance. Okay, so if W over L exceeds 2, the aperture efficiency will begin to drop. Okay, so and another one is, yes, like I said, if you want to match it with the feed line, we can do it by using the inset feed and setting this inset position. So here is how we set the inset position. So we call it recessed microstrip line feed. So recessed means that it just recessed or retreated inside this patch. Okay, instead of staying here, it recessed inside this patch. Okay, to this position. This is a good technique to match the patch antenna with known characteristic impedance. So this graph shows the profile of the input impedance when you set the inset position and position Y0 over when you do not set the inset position or Y equals 0. You see that the relationship between these two resistance follows this kind of like, it looks like sinusoidal to me, but it's not exactly sinusoidal, which you're going to see in the next page. Okay. For that, the microstrip line feed also has its own characteristic impedance. If you put the line feed, okay, and you connect the line feed to the patch antenna, you need to calculate the characteristic impedance, and there are two formulas here. One is used when the ratio of W0 over H is equal or less than 1, and the other is when it is greater than 1. So what is W0? The W0 is the width of your feed line. So it's not the patch width, it's the width of your feed line. So let's see if we can, sorry, here. Okay, so this is your W naught. Okay, but normally the feed line impedance is given in the exam or in the homework or in the practice problem. So you might not be able, sorry, you might not need to determine the corrective impedance here. So for most typical microstrip, we found that the conductance is much less than admittance. Also, the susceptance is much less than the admittance of the sorry, of the patch. So say YC here, it means characteristic impedance of the patch. So finally, the equation here shows the relationship between input resistance when we put the inset position at y0. It is equal to 1 over 2 G1 plus minus G12. So this exists only. There is mutual effect between two slopes, and multiplied by cosine square of pi over L multiplied by y naught. So I'm just going to show you the example here. Okay. So for just a short example. All right. So let's say you. Okay. Let me write it down here. Okay. Let's go back to. Wait. Okay. So let's say, for examples, I may ask you to match the characteristic impedance of the feed line. Okay. So for example, let's say this is 75 ohms. Okay, 75 ohms, the feed line. So let me make sure that I use the right symbol. Okay, same. Okay. So this feed line characteristic impedance is 75 ohms, and we want to match it with our antenna. Okay. So earlier in our examples, we found that our W is 1.186 centimeters, and our L is 0.906 centimeters. Okay. With this information, including the information of FR, okay, then you can use this three. Okay, actually, don't use L. You just use these two. Okay, 2 phi G1 and B1. Okay. So therefore, and actually another condition that we need to check is if H over lambda naught is less than 1/10 naught. Okay, so we need to check if this H over lambda naught is less than 1/10. So H is 0.1588 centimeters times 10 to the minus 2. Okay, make it meters. And then C over F 10 to the 8 here, and 10 to the 10 here. Okay. So we could see that as 10 to the 8, and you get about 0.05262 okay, like this. So this is mean that this is less than 1/10, so we can use this equation. We can use the equation. So you can find G1, okay, by W over 120 naught. 1 minus 1 over 24 K naught H squared. Okay. So from here we get our 0.1866 here. Okay, it's less than 1/10. So now we're going to find this G1. Okay. So G1 is W, which is 1.186 times 10 to the minus 2. Meters 120 times 3 to the 10 to the 8, okay, and 10 to the 10 here. So this is this term is operating wavelet. And 1 minus 1 over 24 K naught. Okay, now we need to find K naught. So K0 is 2 pi over lambda. So our K0 is 2 pi over lambda naught, which is 2 pi, again, C over L3, 10 to the 8, times 10 to the 10, and is equal to 209.44. So we just place 209.44, and H is 0.1588 times 10 to the minus 2 squared, and then we have this. Okay, and this term you'll get something around 0.995, okay, multiplied by the whole thing here, and then you have 0.00328, okay. So at the this is what happens at the conjugate matching. So what happened at a conjugate matching is the total input admittance is equal to 2G1. So just for now, we just neglect the mutual effect. So 2G1 is 2 multiplied by 0.00328, which is equal to 0.00656. Okay, and that corresponds to input impedance of. Okay, let me punch number into the calculator. Is 152.47 ohms. Okay, so this input impedance is the input impedance to our patch antenna. Now, we want to match this patch antenna to the feed line that has 75 ohms characteristic impedance or characteristic resistance. So what we're going to do is that we're going to use this equation. R in Y equal Y naught, okay, equals 1 over 2G1. So now that we neglect the mutual effect, we will only have this 2G1 left in our formula. Cosine square of pi over L Y naught. Okay, I forgot. Okay, so eventually we will use this L, okay, in the calculation, so we cannot neglect L. So these two G1s is, okay, this is 2G1 or 1 over 2G1 is our Rn, okay, as at y equal y0. Because this is our, okay, this is Rn, this is our input resistance, okay, to our patch antenna. And then we did not consider the feed line yet, okay? So, which means that we think of that recess position at 0, okay? Because the position is at 0. So Rn of y equals 0 multiplied by cosine square of pi over L y naught, okay? So now we just place this number, 152.47 cosine square pi over 0.906 10 to the minus 2, and this is what we need to find, the y naught. And then what is this? This is the input resistance when you place the recess feed, or when you put the inside position. So we want it to match with the characteristic impedance of the microstrip feed line, which is 75 ohms, so we place 75 ohms here. And then we just solve this equation. Okay. So it becomes cosine square, the distance, equals 75 over 52.7. Okay, so let me solve both terms. This is 0.492 and is 173.3819. Okay, so cosine 173.3819 is equal to the square root of 0.492, which is 0.701. Okay, and then this is 173.38y0 equal cosine of 0.701. Okay, again, at this point, this is the point that you usually make mistakes. When you do something like this, the argument of cosine is always in radian. Okay, in radian. This is the basic element. It's in radian. So we got this, we got 45.46 degrees, which will be converted into radians, okay, as 0.793 radian. Okay, so therefore this y naught is 1.793 divided by 173.38, and we got 0.00458. Okay, so if you think in the unit as millimeters, it's about 4.58 millimeters. So that means this is your W, this is your L. Okay, your W is 1.186, and your L is I think I did something wrong. Okay. This should be your length, 1096. Okay, and 1.186 here. All right. So this is 9 millimeters. So I'm going to have to place the feet line, okay, in here. And this is around 4.58 millimeters. Okay, to get the matching done. Okay, to get the matching done. All right, so this is the answer. Okay, so this is the basic design of the microstrip lines, and I think if you understand if the steps, all the steps, then you'll be able to design, and actually you can implement the actual microstrip antenna. Okay, with this with this procedure. Okay, so see you again next week. Thank you.